Greetings everyone! Dear U-Info 2021 conference participants, I'm Nenad Petrovic, teaching assistant at the Faculty of Electronic Engineering, University of Niš in Serbia from the Department of Computer Science. Now I'll present you my paper, which is entitled COVID-19 Safety Systems Design Exercises in Computer Science University Courses. At this point, all of us are already introduced to the fact that recent COVID-19 pandemic has had huge impact on education at all levels. Numerous changes of both teaching methods and materials had to be performed in order to adapt the existing teaching processes as much as possible to online form. When it comes to computer science university courses, often their constituent part are practical laboratory sessions which are done using computer, but sometimes they could also require additional hardware devices such as development boards, which are not affordable for all of the students. So the main challenge is actually how to adapt this kind of courses to online form. In this paper, I will focus on the adaptation of laboratory sessions during the COVID-19 pandemic scenario, considered from perspective of two bachelor degree courses that I teach at Faculty of Electronic Engineering for Computer Science track. The first one is microcomputer systems at the third year of bachelor degree, and the second is logic design at the second year of bachelor degree. The current logic design course curriculum is mainly based on Professor Radomir Stankovic's work, which covers the following topics: logic function representation, function classification, functional expansions, decision diagrams, different types actually of decision diagrams, synthesis techniques such as ROM-based synthesis, multiplexer-based, PLA and FPGA, easily testable networks, Boolean difference and its applications, and finally sequential networks. The written exam consists of 4 exercises done in 4-hour time slot. The lab sessions consist of Matlab implementation for the exercises related to the mentioned topics. In this paper, we'll focus actually on 2 of the topics. The first one is synthesis techniques, actually to be more precise, PLA-based synthesis. And the second are sequential networks, actually Moore's automaton. Programmable logic arrays, the so-called PLAs, consist of 2 main matrix-alike elements: AND matrix, which actually generates the product terms, and on the other side the OR matrix, which sums them up. Moreover, there are 3 register elements. The first one is input register, which is used to bring the data to the input of AND matrix. The second is feedback register that connects the output of OR matrix to the input of AND matrix. And finally, the output register, which transfers the output of OR matrix to the PLA's output. When it comes to Moore's sequential machine, it's actually a finite state automaton where the generated output only depends on the destination state during the transition. Regarding the microcomputer systems course, it covers 2 major topics: Intel 8086 base systems on one side and PIC16 family microcontrollers on the other side. The written exam consists of 2 exercises done in 4 hours. The lab sessions initially were done using development boards, but they didn't cover the part related to Intel 8086. So, in these new circumstances, we decided to adopt Proteus design suite, which enables convenient modeling, simulation and execution of applications using 8086 and related components. The course covers several additional components, such as 8255 for parallel input and output and 8259 interrupt controller. In this paper, I focus on the first part of the course related to 8086 base systems, and I will show you the practical example which leverages both 8255 and 8259. The first exercise example is COVID-19 indoor safety system based on 8086 architecture aiming microcomputer systems course. For 3 capabilities, it relies on external systems. We assume that Arduino Uno is used for both the passenger detection and contactless temperature measurement, while Raspberry Pi equipped with camera is used for mask detection. It executes computer vision algorithms written in OpenCV and Python. As a control unit and the core of the system, actually we have 8086, which is responsible for door lock and unlock depending on the visitor's state. 8086 relies on 2 additional components. 8259 is used for interrupt handling when new person arrives and performs the check whether the mask is worn and the temperature is normal. Moreover, we have 8255 on the other side, which shows the current number of persons within the building on a 7-segment display, and locks or unlocks the door correspondingly. Moreover, on this slide you can see both the pseudocode and assembly of interrupt which is executed when new person arrives. Check is performed whether the temperature is normal and mask is worn. If that is the case, another check is performed whether the number of persons currently inside the building is equal to the maximum person threshold. If that is the case, then the person should wait for someone to exit the building. Otherwise, the door would be unlocked and the person count would be increased and shown on display. Otherwise, if the person either has temperature greater than 37 or doesn't wear mask, the door will remain locked. By taking a look at the main code executed on 8086, we can see that 8255 has its port A and B configured in output mode, as port A is responsible for 7-segment display and port B is for door lock unlock. Instead, here we have red and green LED diode that actually corresponds to locked and unlocked door state. Moreover, we have port C which is in input mode, as here we receive the signals which are result of mask and temperature checked received from the external systems. When it comes to 8259, we have two interrupts. The first one has vector 172, which actually corresponds to person leaving the building. So the corresponding vector table addresses are, for instruction pointer, actually 172 times 4 and plus 2 for that value for code segment. For the second interrupt, we have vector 173, which is actually the person arrival, and it is calculated by multiplying by 4, and it's 692. We add 2 to actually get the code segment value for the second interrupt. For these two code segment in instruction pointer values, we use the following macros in assembler. For code segment, we actually execute by telling the seg and the name of interrupt procedure, and for instruction pointer we say offset and the name of the interrupt procedure. In what follows, we'll see live demo in Proteus. So, when new person arrives, which is acknowledged by pin number 5 interrupt line on 8259, the number of persons inside the building will increase by 1 and will be shown on 7-segment display if both the temperature and mask checks are passed. So, for temperature and mask check, we have pins PC0 and PC1 on 8255. Green LED means that the door will be unlocked. So, if one of these two checks fails, the door will remain closed and the red light will be turned on. So, if we actually turn back the mask check as passed and new person arrives, the red LED will be turned on and number of persons will remain increased until the threshold of maximum persons alive within the building. So, when it arrives to 5, no more persons will be allowed to enter and red light will be turned on. So, if we take a look, there is one more interrupt line used, which is number 4. So, actually, it is triggered when a person exits the building. So, the number will decrease from 5 to 4. Let's take a look at the main part of the interrupt code, which is responsible for these checks. So, here we have two interrupts. The first one is actually handling the exit of a person and decreases the number which is shown on display, while the second one performs the checks and unlocks the door in the case that both checks are passed and the number of persons is below 5, as you can see. In what follows, we'll see the same problem solved from the perspective of logic design course using PLAs and Moore's automaton. So, the three main elements of Moore's automaton are the inputs, states and outputs. When it comes to the inputs, we have 4 possible inputs. The first signal is new visitor's arrival, which is decoded as 00. Moreover, we have temperature normal signal, which is 01. We have mask wearing signal. Actually, the person has passed the mask check. It's 10 signal. And in case that any of these two checks fails, we have the fail signal, which is encoded by 1, 1. We have 4 possible states in Moore's automaton. The first state is S0 and denotes that we have to wait until new person arrives. The second state is S1. In the case when new person has already arrived, we can perform the check. The first check is actually the temperature check, and it's in the state S2. And in S3 we have the must check past state, which is actually the final state. So when both the checks have passed, actually the generated signal will be 1, which means that the door will be opened. It's one of possible output signals, while the second is in all the other states from S0 to S2, and actually means that 0 corresponds to entrance closed. However, in case that any of these two checks fails, we'll go back to the state waiting for new person's arrival. On this slide, we'll see the PLA-based implementation of the previously described model. Before doing any synthesis, we write down the transition table. It describes what are the transitions made from one state to another when certain type of input arrives and the generated output on the other side. On the bottom left, we can see RS flip-flop, a transition table which is used as auxiliary element for this implementation. According to this, we write all the columns from R0 to S1. Moreover, we use the sum of products form for each of these columns and use them to connect the elements in and or matrices of the PLA. On bottom down, we can see the whole implementation using both the PLA and RS flip-flops. Another type of exercise which is also possible to be done on laboratory sessions is actually the Matlab implementation of automaton verification of the previously described solution. So it is possible to use the matrix representation of transition state matrix as shown on the left side and use the Matlab code from the right side in order to verify whether there is a state which is unreachable in this finite state automaton. Now we'll see the Matlab code live in action, checking whether the previously described automaton has a state which is unreachable. In that case, it will return 1, otherwise it returns 0. So we use the matrix representation as previously described and it returns 0. So it means that the verification has passed. When it comes to the future instances of logic design course for new accreditation, our plan is to adopt active HDL simulation and modeling tool, which is actually moving towards HDL-oriented design. So here it is possible to specify finite state automaton using graphical interface and translate it to HDL code, as you can see on the right hand side. Now you can see the previously described state machine defined within active HDL environment. So to each of the states we have output value assigned, and for each of the transitions between states we have the conditions that need to be fulfilled in order to perform that transition. When we generate VHDL code, we get the following script. So this script can further be used for any kind of synthesis which is supported by active HDL, such as FPGA, PLA and so on. To sum it up, the proposed approach has really many benefits. Not only that we have transferred the existing laboratory sessions to online form, but also the goal was to make the engineering students aware of their possible role during the COVID-19 pandemic battle. When it comes to students' involvement, it was also increased, as previously microcomputer systems course didn't cover 8086 base systems, as we didn't have the corresponding development boards. When it comes to the future work, we'll be working on adapting these courses to new accreditation requirements. Logic design will go towards HDL-based design, while microcomputer systems would evolve into IoT-based course, where the topics would cover modern ARM-based microcontrollers, Arduino Uno, and Raspberry Pi single-board computers. This work has been supported by the Ministry of Education, Science and Technological Development of the Republic of Serbia.